Did you ever write an especially nice bit of code in Rust? Code that is well designed, concise, and just all around quite nice, but then you compile it and you find that the borrow checker won't accept it. You start fighting the compiler, change things around a bit, but the compiler just keeps refusing your code until you really want to just have some lobster for dinner because you're just that frustrated. This or something like it has happened to me on a few occasions. Especially when I started out coding in Rust, I would spend a lot of time fighting the borrow checker and trying to figure out why it rejected my code. Sometimes the borrow checker really was trying to stop me from doing something bad, like introducing a use after free error or another bug. Often this was not the case though. Usually I knew the thing I was trying to achieve was in fact memory safe. In these cases the error could usually be solved by refactoring my program. Often this would involve actually creating a new struct and moving the offending functions and variables into that struct. Today I would like to take the time to investigate some of these examples. First we'll take a look at the actual examples, and then we'll discuss why moving things into structs is a strategy that can work to stop fighting with the borrow checker in Rust. Hopefully this will help you get productive with Rust a lot faster. It should also allow you to avoid some of the pitfalls I ran into when I started learning Rust. You can find all the code in the text version of this log down in the description. On the techniques I'm going to discuss in this video. They only really work if the thing you are trying to achieve is actually possible under the limitations of safe Rust. This won't help you, for instance, implementing a doubly linked list, because this structure really requires you to have multiple references pointing at the same location in memory. And this is something the borrow checker generally prohibits for good reason. You will still need unsafe code or reference counting in these situations. Here is our first example. Basically, this is just a simple demonstration of using a global variable, except that it's broken. Line 3 here will cause the compiler to fail. It will say, calls in statics are limited to constant functions. What this means is that the initializer must be one that can be executed at compile time. Many functions can be constant like this, as long as no system resources are used. But how are you going to allocate memory or read a file from the system during compile time? The answer is you can't, because we don't even know yet which system this application will be run on. The vector from initializer needs to allocate memory, so that simply can't be used. Here's how I fixed it. Instead of vector from, we are simply going to use vector new. This creates an empty vector which does not involve allocating memory, so vector new is alright to use. We just have to add our data later when the program starts. For this purpose we made our static variable mutable, and we'll also add this extra function to add the data. This new code works. It will compile and it will print our vector now containing 42. You may have noticed that adding our data and printing the array is wrapped in an unsafe block. Of course, that is not very good. We don't want any unsafe blocks. But why did we have to add that block? Rust stops us from accessing static mutable variables because of thread safety. This example is a single-threaded application, but you could be running multiple threads. If any one of those threads changes a vector while our main thread is printing the variable or otherwise accessing it. In this scenario, our main thread could not just see the state of the vector either before it was changed or after. Our main thread could see an intermediate state, or due to the way modern CPUs work, our main thread could see a variety of broken states which are entirely different. So broken in fact that our program could crash. Our particular example would work, but because Rust prevents us from doing dangerous things, it prevents us from using mutable global variables in safe code. Here's the same code with both issues fixed. We start out by declaring our struct, which contains all the global variables as fields. The initializers have been moved inside the struct constructor. The actual code of our application was made into a member of the struct, and our main function now just takes care of creating the application struct as well as invoking the main function. Using a struct in this case allowed us to get rid of unsafe code blocks, and it enabled us to use a non-constant initializer for our global variable, which is in fact no longer a global variable at all. Now let's continue with our second example. You might have guessed what this is supposed to do from looking at it. It takes a list of samples and adds a new measurement to that list. It only does that if the sample is not an outlier. That means, in this case, if the value is not too far outside from the range of previously sampled values. This example is mainly concerned with aliasing. In this case, our aliases are 3 closures. Could be plain references too, works pretty much the same way. One closure is concerned with calculating the average of our samples. A second is used to compare how large the size difference between 2 values is. And a third closure tests if our value is an outlier. These aliases here are very useful because they make our function a lot more readable. Think about it. Would you have been able to get that the jumble of code that calls the default function is supposed to calculate an average? Aliases help us give names to concepts which would otherwise be just some opaque code. They also let us reuse code in a very concise way due to their short names. And again, unfortunately, our code won't compile. Our average closure requires a reference to samples. This means it is no longer available for borrowing later when we try to call push. Let us now fix this by adding a struct. This time we move the state of our function into the struct, which in this case just happens to be every argument that function takes. We turn the aliases, the closures, into the structs methods. Finally, our original function now contains code to create the temporary struct as well as the original logic. We could also add an extra method, addSample, into the struct and just have our primary function call that. Either way works fine. Using a private struct allowed us basically to keep using our aliases. Besides that, the code is also a bit more verbose, but it could be worse. There also would have been other solutions to this issue. We could have made average a proper free function. Doing so would probably have made the function a lot more complex. We would have to make it generic, make it accept any iterable, and decide on the proper way to deal with an empty list. This version is much easier to implement because it is tailor-made for one specific use case. Moving on to our final example. This time it's about a function taking 2 closures, handling errors and warnings respectively. Both closures store a reference to the cursor, which of course is forbidden by the borrow checker. We already know how to fix this with structs. That is not really the interesting thing here. Turning these 2 closures into a struct, though, gives us a pattern that is quite famous. It's called the visitor pattern. This is a generic interface, a trait where basically each method can represent one event. This construction is extremely useful because pretty much any problem can be modeled as a sequence of events. JSON, sequence of strings, integers, keys, object starters, object terminators, and so on. HTTP server, sequence of requests. Searching a file system, sequence of files, directories, and links. Since we already looked at a basic example of moving closures into a struct, I decided to create a more complex example using the visitor pattern. This example is there to encode JSON. As you can see, it is a bit long. I'll post the link down in the description so you can take your time reading it. This time we first start out defining our trait with all the events. Then we move on to our implementation, the actual visitor, which is a generic struct in this case. It holds a writable stream and some extra data. Next we implement some helpers, and then we go on to implementing the actual event handlers for our visitor. Then we go on to adding a function example JSON that encodes the structure of our document and a main function that glues it all together, creating the output stream, the visitor, and running example JSON. What is so nice about this construction is how flexible it is. We could replace either the emitter of the event sequence, example JSON, or the consumer. We could also, for instance, build a visitor that somehow changes the event stream on the fly and forwards it to a second visitor. Our emitter could be fixed, like in the example, or it could be dynamic, parsing an actual JSON document. Actually, we're not even bound to JSON at all. We could write a generator that encodes YAML, BSON, or another format that uses those primitives. The performance is great too. This is just a couple of method calls, one of the most basic operations there are. Usually I don't particularly like design patterns. I think they are something that should only really happen after you've written a piece of software and notice that some part of your code looks pretty similar compared to some other piece of your code. As far as design patterns go, however, visitors are pretty neat. Certa, the great Rust serialization framework, is using a visitor internally. One thing you may have noticed in these examples is that they kind of are about cases of ad hoc coding. So with those being dirty solutions, except for the visitor example, with those being dirty solutions, why don't we just refactor our code to use proper solutions, whatever those are? I would argue that in a great many cases, these ad hoc coding solutions are also the best possible solution for any practical engineer. Adding a proper function with all the requirements of being generic, well-tested, well-documented, and specifically with the requirement to accept any possible input without undefined behavior. With all those requirements, adding a proper function can be a lot of work. Sometimes that's just not worth it. Even if we decide all the effort is worth it. Enlarging your API means making it harder to understand your API as well as making it harder to maintain. It also means features are going to be harder to change later on and remove because they are part of your API. Premature abstraction has been the bane of a lot of software projects. Object-oriented development has taught us a certain idea of what an object should be. For instance, that it should have no public fields and that it should be part of your API. I urge you to let go of that notion. A great API is much more and much less than a list of structs contained in your library. So I'll say keep using those ad hoc solutions, maybe just move them into a struct if you're coding in Rust.